So, hello students, welcome to this lecture on VLSI design KEC 072. This is lecture number 23. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. So, in this lecture, we are going to continue our discussion on various alternatives which can be used to obtain a low power VLSI design. Plus, we are also going to introduce the concept of fault in a digital circuit and how we can identify these faults. Okay. So, let us start. The topic which we want to discuss today is known as adiabatic logic circuits. Okay. So, the approach still remains the same, that we want to obtain a circuit which consumes less power and maintains its functionality. Okay. Adiabatic as a term, in true sense, it is not an electrical term, it is a thermodynamic term. It is used in thermodynamics to describe a system or an object which does not lose energy to its surroundings. Okay. So, if it does not lose its energy, okay, we might be able to use such kind of an object or a system or an arrangement to actually produce a low power design. Okay. So, it is an alternative approach which is focusing on reducing the switching activity. Okay. So, so your digital circuits can switch between 0 to 1 and 1 to 0. If you can reduce that switching activity, you will reduce switching power, and if you can reduce the amount of switched capacitance, how much capacitance interchanges, while charging how much it increases, while discharging how much it reduces. Okay. If you can control that to a certain level that it does not affect your functionality. Okay. So, logically at the same time it is going to affect the power consumption also. So, we already know how average power depends on parameters like load capacitance, clock frequency, square of supply voltage, and there is one more parameter which is known as alpha t. This is nothing but the node transition factor. So, if your switching takes place in one clock cycle, alpha t is 1, but if it takes multiple clock cycles for one switching exercise to take place, then alpha t starts to increase. Okay. So, for n number of clock cycles, if that are taken, alpha t starts to increase. Right. So, it basically measures how many cycles of switching are required for one particular or the designed operation to take place. Right. So, what happens in any CMOS circuit, whenever you supply energy or power source, okay, which is usually a constant power source is there, constant voltage source is there, it charges your load capacitance, okay, and it keeps it charged to a certain value, and then at some time depending on the logic it can discharge also. So, whatever power you are supplying, okay, suppose you supply power which is the load capacitance time square of VDD, half of it, let us say half of it goes to the load to charge it, half of it can be dissipated in the PMOS also while your signal is being pulled up, okay. And the other half, when the signal is being pulled down, output is being pulled down, this load capacitance, whatever is in the load, that amount of power can discharge. So, whatever you have supplied, it lasts only one clock cycle while charging and while discharging. Okay. So, for the next cycle you have to supply some power, right. So, this switching activity which is taking place from high to low or low to high, okay, that is also consuming power from the source. In this direction, if we think about it, what if some of the supplied power, it can be sent back to the source, okay, which means if we can recycle this power. First, try to minimize power consumption, and whatever you have extracted from the source, try to send back some of it. In that case, obviously, the design is going to be a low power design. Okay. This is the theme, this is the background or the basis for an adiabatic logic circuits. Okay. So, power dissipation can be reduced if you try to minimize the number of switching events, if you try to decrease the node capacitance. Okay. The node can be an internal node, external node, your load capacitance, reduce the voltage swing, or apply a combination of all these methods. In all these cases, the energy which is drawn from the power supply, okay, is used only once before being dissipated, okay, but there is no recycling. Okay. So, basically these approaches you can sort of reduce the amount which you are consuming, but you are not sending anything back. Adiabatic logic circuits, they offer the possibility of further reducing the energy dissipation. Okay. So, you can minimize the switching events, you can only charge your nodes to the minimum required value of capacitance, you can reduce your voltage swings, you can use a combination of these, that reduces power dissipation, okay, but that does not do power recycling. Adiabatic circuits, they offer an extra bonus kind of thing, they reduce the energy dissipated during switching events, and it also provides a possibility of recycling or reusing some of the energy which you have drawn from the power supply. Okay. So, consider this RC circuit here and we are charging it through a constant current source. In a normal CMOS circuit, your load capacitance or any capacitive node will be charged via a constant voltage source. Okay. In this circuit which is shown here, the RC circuit is actually being charged by a constant current source, okay, and this is similar to a voltage ramp, right. So, try to see we are analyzing a circuit, an RC circuit, RC passive circuit, which is not being charged by a constant voltage source, but it is being charged by a voltage source which has edges which have a certain slope. Okay. So, it is ramping up or ramping down, the voltage source is ramping up or ramping down and both, and then it is charging the RC circuit. In such a circuit, we can say that the energy dissipated, there is a small method for deriving this expression, okay, but this dissipated energy while charging up is given by RC by T C into Vc square, which is a function of time t. Okay. So, R is the resistance, C is the capacitance, T the uppercase T here is the time for which you are basically charging your circuit, okay, and Vc is the voltage across the capacitor, which is a function of time. A portion of the energy stored in the capacitance can be reclaimed if you reverse the direction of current source, and in a ramped voltage source, if you see the upgoing ramp, you might be charging. If you see a downwards ramp, okay, a ramp with a negative slope with respect to time, in that case you might actually be sending some power back. Okay. Adiabatic logic circuits, in this case they are not going to use your standard constant voltage source, but they are going to use a power supply which has a time varying value of voltage, the so called pulsed power supplies. Okay. So, something like this. So, your power supply can go up, can remain constant, come down. Okay. So, this is time t and this is voltage. This kind of a voltage source is known as a pulsed supply. Okay. It has a certain ramp, it has a certain slope to it. So, while going up it might charge, while going down not all the power gets dissipated, some of the power comes back to the source. So, this kind of a arrangement can produce what is known as an adiabatic logic circuit, which helps you to do some power recycling, okay. And that is our basically main aim, to produce a low power circuit, and if you are able to send some power back, you are basically reducing your consumption only, right. So, to convert a conventional CMOS logic gate into an adiabatic logic gate, the pull up and pull down networks, they must be replaced with complementary transmission gate networks. By now, we should know what is a transmission gate. It is a circuit which is basically a combination of both P type and N type MOSFETs in such a way that the circuit at the input will go to the output either way, okay, if both the PMOS and NMOS are on, and the PMOS and NMOS will be operated with complementary clock cycles. Okay. So, you can have an arrangement something like this. So, you can have a PMOS here, right, and you can have an NMOS here. This NMOS can be driven by clock, PMOS can be driven by clock bar. Okay. So, whatever is at the input goes to the output if your clock is high. If it is a 1, it goes through, if it is a 0, it goes through, and they go through at the same intensity. Okay. So, basically NMOS passes some logic signal with great strength, PMOS passes some logic circuit with great strength. So, both are used. This is a transmission gate, right, and you use a complementary transmission gate networks instead of your normal pull up and pull down networks. Okay. If you replace your conventional pull up and pull down network with a transmission gate network, you are moving towards an adiabatic logic circuit. Okay. The T or the transmission gate network implementing the pull up function is used to drive the true output of the adiabatic gate, while the transmission gate network which implements the pull down function, it drives the complementary output node. Okay. So, this is something still on the lines of a typical CMOS design only, right. All the inputs, they should be available in both the forms, standard and complementary. Okay. So, if you have two inputs A and B, A bar and B bar should also be available. This might increase some overhead cost, you might need some more inverting circuits, but that is a very small expense considering that you are able to recycle the power. Okay. Both networks, your T gate pull up and T gate pull down network in the adiabatic logic circuit, they are used to charge up as well as charge down the output capacitances, which ensures that the energy stored at the output node can be retrieved by the power supply at the end of each cycle. So, see what we are doing here? We are basically doing some kind of a recycling operation. First thing what we did, we replaced the normal voltage source or constant voltage source with a pulsed power supply, okay, which has a certain ramp type behavior to it. So, with respect to time, the voltage can ramp up or ramp down. Okay. Then instead of the standard pull up and pull down network, we have used complementary transmission gate networks. One transmission gate network does the pull up function, okay, for the true output, while the other transmission gate network does the pull down function for the complementary output. Okay. All inputs, well, as I have said, they should be available in complementary forms, okay, and both the charging up and charging down can be done for the output capacitance, okay, so that some of the power comes back to the source and gets recycled, and our objective of low power VLSI design is achieved. Okay. So, let us see this example here. This is an adiabatic CMOS and or NAND gate. Okay. This circuit which you see on the top, so you have two inputs A and B. A bar and B bar is also available. So, you have A bar, B bar and A bar here. So, the inputs are available in complemented and true form, right. Instead of standard constant voltage source, we have a pulsed voltage source which can ramp up or ramp down, right. So, while ramping up, it can run some of the signal, while ramping down it can send some power back to the source. The series network, there is a series network here. Okay. So, you have a series network of transmission gate plus you have a parallel network. Of T gates. Okay. The series network, it is basically performing the AND operation between A and B. Okay. So, when both A and B go to 1, your signal gets transmitted and your output gets charged. So, you get a 1 here. Okay. So, if you put A equal to 1, if you put B equal to 1, this transmission gate is on, this transmission gate is on, output gets connected to the voltage, it can ramp up and it can get connected, okay, and get charged to a logic 1 value and gives 1 at the output, an AND circuit. This on the other hand here works as a complementary NAND function. Okay. So, if you put A equal to 0, B equal to 0, this turns on, this turns on. Okay. So, if A is 0 here, this is on, if B is 0, this is on. Right. In that case, your V out bar gets connected to V A and you get a complementary NAND function. Okay. So, your pull up network, as you have seen in the previous slide, what your pull up network does, or the transmission gate network which is performing the pull up function, it is used to drive the true output, while the transmission gate network which is implementing the pull down function, it drives a complementary output node. Okay. So, you get the complementary output here, right. So, this is how you are basically converting or transforming a typical CMOS circuit to an adiabatic circuit, and because of this power recycling in the other half of the cycle, some of the power can come back to the source also, right. In that case, you are actually producing a low power VLSI design circuit. Okay. So, this is all about adiabatic logic circuits. Okay. Going forward, now I want to introduce the concept of how you can test your circuits, integrated circuits, so that it is defect free, it is fault free. Okay. So, by now we have introduced the concept of low power design, we have seen the implementation techniques. Now, once we have a design ready for us, we want to identify either at the circuit level or the device level or the system level, whether my integrated circuit is defect and fault free or not. In order to have smooth functionality and defect free circuit and devices, the testing and observability of ICs need to be done, or these techniques, the ICs need to be grown for deep submicron technology. Technology enhancement and higher complexity of IC can act as an issue when you want to do testing as well as obtain faster clock speeds. Okay. The demand for things like delay testing and timing analysis is increasing quite a lot when your operating frequency goes up and you scale down your devices. Okay. There are generally 3 ways by which you can test your circuits. Okay. These are broad classifications. Verification testing, if you want to test the correctness of circuits and devices. Manufacturing testing, if you want to test for any logic faults, parametric faults and physical faults which can occur during the manufacturing stage. Okay. And acceptance testing, which is once you have the finished product supplied by the VLSI industry, these need to be verified and accepted by the user only once your acceptance test is clear. Okay. So, with the definition you can have a small understanding that these tests are actually working at different levels of abstraction. Okay. So, you are verifying the circuit and devices, which is can be considered as an initial stage. You are testing for different faults during manufacturing, okay, and then you are testing the final process device also or the product also. Okay. So, these are the so you can say that testing is a very comprehensive process which can be applied at different levels of hierarchy. Okay. And now, what is fault modeling? A fault model is an engineering representation of something that could go wrong in the production, development or operation of a circuit or device. Okay. So, first you identify fault and then you devise a model which actually helps you to isolate that fault and correct it. That is fault modeling. Okay. Fault modeling is not the fault by itself, it is a mechanism by which you can simulate what can go wrong or how your device or circuit can be faulty. Using such models, the designer or the user can efficiently and effortlessly predict the consequences it might have of having that particular fault. Okay. It is kind of having a standard library of faults, okay, where you can apply these modeling tests and find that this particular test from the library is the reason behind the failure of any circuit. Okay. So, instead of listing the types of faults, the basic essence is to describe the impact on the normal operation. Okay. It is like creating a database of the effect of faults on the VLSI circuits. Okay. The number and nature of faults in any VLSI circuit is strongly dependent on the level of abstraction. We have already seen the classification of different types of test. Okay. From that it was clear that testing can be done at different level. In any VLSI design, you can have different levels of abstraction or modeling. You can work on the system level, you can go slightly down, okay, which is known as the RTL or the functional level, okay, where you have done the interconnection. You can go to the logic gate level also, which is your you can consider it is your structural level, a structure of gates is created. The gates are produced from transistors only, that is another level in hierarchy. And finally, you can go to the physical level where we are actually considering how much silicon is required, what are the material properties and all. So, from left to right you are basically increasing the level of detailing which is required for description. At the system level, you might have a packaged device, but that does not offer you a lot of information about the system, about what is inside this system. If you move towards from system level to RTL to the structural gates to the transistor to the physical level, you are going down on the hierarchy, you are increasing or you are reducing the level of abstraction or you are increasing the level of details. The amount of information provided at the system level is way less than what is available at the physical level. These are the two extremes. At the system level, the number of faults are relatively less and fault modeling is very easy, but the overall result of fault modeling may not be reliable. As we move towards the physical level, the number of faults increase significantly, fault modeling becomes very difficult, but the results are more accurate. So, in terms of detailing, you have very less detail here, a lot of details here. You have very less faults here, you have lot of faults here. Fault modeling is relatively easy here and it is quite difficult here. So, between these two extremes, rather than going to the extremes, it is better to work somewhere in the middle. Why? Because it is more of an optimized approach, where you are able to identify almost all the faults without spending a lot of effort and cost. At the highest system level and lowest physical level of abstraction, fault modeling reaches an extreme, that is what I just said. At the functional level, defect which causes the fault, the identification of that defect is challenging. So, we need an optimized level of fault modeling, which is generally done either at the logic level or the device level. So, either at the logic level or at the level of the transistor itself, the device itself. Here, if you are able to do fault modeling, you have basically zeroed in or isolated almost every fault, plus the process is relatively easier and the result of fault modeling is also accurate. So, most of the fault detection, identification, modeling or removal process is generally focused around either the gate level or the transistor level in the hierarchy. And this is where you basically include both, you include the device and you include the circuit as well. So, you are able to isolate a majority of the faults at these two levels. So, most of our fault modeling analysis is going to be focused at these two levels of abstraction. At the logic level, you have two common faults. These are known as, now there can be more also. I am not saying that these two are the only faults possible at the logic level. But most commonly you have these two faults only. One fault is known as stuck at fault. Stuck at, as the name suggests, that a particular line in your circuit is stuck at a particular logic value. So, you can have, suppose you have a circuit, you have an AND gate, a 2 input AND gate, this is driving an OR gate, which is taking another input, and you have another circuit where you have an OR gate, 2 input OR gate, being driven by another input. So, you get your output here and you get your output here. Suppose this line here, because of some fault, and that fault can be anything, your gate oxide can have a hole through it, some kind of a short circuit, a metal short or a gate to metal short. And based on that defect or fault, this point here, this intermediate point here is at logic 1. Does not matter what is A or B, this point always remain at 1. So, I would say that this line is stuck at 1, because it is driving an OR gate, my output will always be stuck at 1. This type of a fault is known as stuck at 1 fault. Now, whatever you provide input at A, B or C, your output always comes out at logic 1, right. This is a stuck at 1 fault. In this circuit here, suppose because of some defect, this point is at logic 0. Because it is driving an AND gate, if one of the input is 0, the output is always going to be 0. Okay. Now, does not matter what you apply at A, B or C, your output always comes at 0. So, I would say that this circuit has a fault which is known as stuck at 0 fault. To identify a stuck at 1 fault, suppose I apply 0 here, I apply 1 here and apply a 0 here. Okay. Logically, I should get 0 here, I should get 0 here and output as 0. But if I get an output 1 here, it means the problem lies here. So, what I am doing? I am designing a model. I am giving you a test case, a test structure. Okay. So, you apply logic 0 at A, you apply logic 1 at B, you apply logic 0 at C. So, 0 1 0 is a test case. This test case helps me to isolate that this line here is stuck at 1, okay? Because when C is 0, the output of this OR gate is dependent on this input, right. And since this is coming from an AND gate, if one or both the inputs are 0, I should be getting a 0 here. But what I am seeing here is that I am getting my output as 1. So, this is your fault modeling. You are trying to simulate your circuit in such a way that what particular type of fault might be existing and where it might be existing. Similarly, in this circuit, if I apply A equal to 1, B equal to 0 and C equal to 1, logically I should get a 1 here, there is a 1 here. So, my output should be 1. When one of the input of an AND gate is 1, the output depends on the second input. That I have deliberately made 0 or simulated it to be 0, but I am still getting my output as, sorry, this I have simulated deliberately to get a 1 here, but I am getting a 0 as the output. So, this is a stuck at 0 fault, and the way, and this test case 1 0 1 is a test case which helps you to simulate or create a model to identify and locate a stuck at 0 fault. Okay. So, these are very common faults, stuck at faults, okay. And the most common model, as I have said, is a single stuck at fault model. Now, a circuit can not necessarily have a single stuck at fault only, it can have multiple stuck at faults. Okay. So, you say whenever a particular line is permanently fixed at logic 0 or 1, that is a stuck at fault. Okay. Similarly, a bridging fault is something where two or more interconnects or wires, they accidentally get connected together, either while designing or manufacturing or just by wear and tear. Okay. So, it can produce a particular logical operation which you did not design. So, two wires which are carrying a particular signal, they connect in such a way that they produce a logical operation. Now, that logical operation, when they connect, that does not necessarily mean a short or a open, it means a bridge. Okay. So, some of the bridging faults can actually produce an accidental OR operation called a bridged OR, or they can accidentally produce an AND operation also called a bridge AND. Okay. So, these are two of the common faults which occur at logic level. In the subsequent lectures, we are going to obtain some models, some processes or test cases where you can actually identify and locate the location of these logical faults. Okay. So, with this we come to the end of today's lecture. We have covered a topic on adiabatic logic circuit, where we produce a circuit, a CMOS circuit with reduced power consumption via power recycling. Okay. So, some of the power is sent back from the output back to the input. For that, instead of a constant voltage source, you use a pulsed supply. You need your true and complementary inputs, and your CMOS gates are replaced by a transmission gate network. That kind of an arrangement produces the pull up and pull down effect and also allows energy recycling. Secondly, we have introduced the concept of faults, okay, and we have seen that most of the fault occur and they are modeled at the logic level or the transistor level. Okay. And we have given you two types of common logical faults, one is stuck at fault, another is bridging fault. In the next lecture, we are going to continue our discussion on fault modeling. Okay. Thank you.